Hi, welcome back to the Alkene Edition playlist in organic chemistry. My name is Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. It's very much appreciated. In this video, we're going to go over a type of addition reaction called Anti-Markovnikov Hydrohalogenation. Okay, now if you look at this first reaction right here, this is one we saw basically in the previous video, or one of the previous videos. This is where we basically took an alkene, and then we subjected the alkene to one of our hydrohalogens. And those included, if you remember from the previous video, hydrochloric acid, the one that's shown there, which is hydrobromic acid, and we could also use hydriodic acid. We put this in the reaction mixture with the alkene, right here, and we note that the bromine atom is actually going to add to the side of the double bond that's more substituted. Okay, the hydrogen goes on the side that's less substituted. Okay, now you can see the product shown right here. Bromine's on the more substituted side, and whenever we look at this group right here, this group, if this group adds to the more substituted side, then we say that's a Markovnikov addition, and it satisfies Markovnikov's rule. We talked about that in a previous video as well. But suppose when we're doing synthesis of some compound, suppose we don't actually want the bromine to add on the more substituted side. What if we actually want it instead, we want it to add on the other side, right here, on this side of the double bond, the least substituted side. And you see it right there in the product. The question is, how do we get from the alkene to this? Now, you can look at the reagents we used for the first Markovnikov reaction. You can rationalize that we can't use that. We're going to have to use a different set of reagents, and we will. The question is, what are they? And I'll go ahead and give you a preview of what they are. Basically, what we're going to have to use is we're going to have to use something called an organic peroxide. We'll talk about the properties of those in a minute, and then we're going to heat that up. And once we do that, then we're going to throw in the HBr. And the difference between the reagents in this first Markovnikov reaction and the second anti-Markovnikov reaction is that in the first one, when we want to add to the more substituted side, right here, we simply add HBr. However, if we want the bromide or bromine atom to add to the least substituted side, therefore anti-Markovnikov, then we're going to have to put the HBr in with an organic peroxide and heat. So that's what this little delta sign means. That means we're going to heat that reaction mixture up. Okay, so that's the basics of it. At the end of the video, we're going to look at a few practice problems, get some practice with it. But for now, we're going to just do some very general things. Okay, now, this right here is an organic peroxide. So what exactly is a peroxide itself? Well, the peroxide itself is literally just an oxygen-oxygen single bond. Okay? So if these right here, these two R groups, R and R prime, were just hydrogens, then that would be what we would call just hydrogen peroxide. You've probably seen this molecule, perhaps. That's hydrogen peroxide. But if we have R groups on either one of these oxygens, at least one, then we term that an organic peroxide, because when we're talking about R groups, carbon chains, those are organic. Okay, so that's an organic peroxide. Okay, so just to get that clear. Now, one thing, and you can learn about this in either general chemistry or P-Chem, whichever one. One thing you'll learn is that oxygen-oxygen single bonds, these are very weak bonds. They're not strong, and they're also pretty high energy. Okay, which means, for example, if I have this hydrogen peroxide, if I were to subject it to heat, really high temperatures and heat it up, or I was to subject it to light, if you haven't seen this before, HV is just is the meaning of light. Okay. Or this really is not a V. Most people say that it's actually the Greek letter nu, but HV, okay. So either heat or light, what you can actually do is cause this oxygen-oxygen bond to break, okay. Now, I'm going to put a little stipulation on this, okay. Whenever we've drawn mechanisms before where, bonds break, so far we've only seen two electrons moving in the same direction, okay. So let me illustrate that point. If we have a nucleophile, right, and the nucleophile is, of course, going to attack an electrophile, right? Remember that what happens technically is this lone pair, which is two electrons, the two electrons attack the electrophile. And if it had a leaving group, then you could potentially get loss of the leaving group. Okay, so that's an example of a nucleophile. It's when you have these two electrons here that can, usually a lone pair, or in some cases a double bond, but they can attack an electrophile. Another example, here's water, lone pair, two electrons, right? Two electrons can attack the electrophile. Okay, here's a bromide, anion, two electrons in that lone pair. Again, the lone pair can attack the electrophile. And in some cases, maybe you actually have a leaving group. Okay, so that's the key with nucleophilic attack. You have two electrons, either in usually a double bond, like a pi electrons, or a lone pair, and the two electrons attack the electrophile, and then either they just attack and it makes a bond, or you get loss of a leaving group, or something like that. Okay. However, whenever we're talking about things of the oxygen-oxygen bond nature, we're talking about actually a different type of electron movement. Okay, here when we're talking about nucleophiles, almost always we're talking about two electron movements. Okay, transfers of two electrons. However, we can actually have a very different type of electron movement where we can actually have something called, sometimes I call it radical attack, or they're just called one electron transfers. The key with radical, when you see this word radical in the context of organic or any other type of chemistry for that matter, you'll see them in biochemistry too, these radicals are one electron. Okay, by themselves. So what does that mean when they're by themselves? Well, I'll draw you an example. Okay, if we look at bromine right here, what I'm going to do is I'm going to draw bromine with, instead of 4 lone pairs, which is what's shown here and having a negative charge, I'm actually going to put one of these right out there. Okay, right out here. Okay, and it's all by itself. So you imagine there's some orbital right there that contains those 2 electrons, some orbital right there that contains those 2, another one that contains those 2, and there's also another orbital over there, but notice, this orbital only has 1 electron. This is, by the way, atomic bromine. So you would say this right here is a lone pair, this is a lone pair, this is a lone pair, but this right here, this is a free radical, or just a radical. Now, radicals are very reactive, but the key is they're just electrons in one electron in an orbital all by itself. Okay, so an example of seeing one on an organic compound, this right here is a propane radical, and right here, notice you see this lone electron right there on the central carbon. So the carbon has 3 bonds, and then it has 1 electron right there. So the carbon's actually neutral. Okay, now what can happen is the 1 electron can actually couple with another lone electron. Now, one thing that's really important here, okay, and I actually didn't have this in the video, I don't think. Let me just make sure. I don't think I put it, but I'm just going to illustrate this right here. Whenever you do nucleophilic attack, I want you to notice something very important. Notice that the arrow that you're drawing, where the electrons are going towards, notice that the arrow has 2 hooks. What does that mean? Well, if I have an arrow that has no hooks, it just looks like that. An arrow with 1 hook looks like that, and with 2 hooks, it looks like that. 2 hooks, 1 hook, 0 hook. You'll never see the 0 hook, so don't even worry about that. The 1 hook, this is called a fish hook arrow. This is what you use to draw radical mechanisms. This is what you use for radical mechanisms, and then 2 is what you use for what they call nucleophilic attack. Okay, so fishhook arrows are for showing 1 electron moving. So if I want to show this electron coupling with this one right there, then what I'm going to do is I'm going to have this radical come out there. That's 1 electron movement, therefore the fishhook arrow. This one will also have a fishhook arrow, okay? And when you draw 2 of these fishhook arrows coming together, that implies that you're forming a bond. How exactly does that work? Well, remember, each covalent bond is 2 electrons. One's coming from this propane radical, the other's coming from this alkyl radical, this R group. So when I draw this, I'm going to get this. Here's the hydrogen, and then I'll draw the bond in yellow because that was what I did, the 2 electrons. And then here's the R group. Okay? And so this type of radical mechanism is just called a coupling reaction. And there's a reason I'm showing you this, and you'll see why in a minute, because when we look at the mechanism of this reaction, you haven't covered radicals explicitly yet. That's going to be covered in a couple chapters after we do alkynes. Then we'll do radicals, and it'll make a lot more sense then. But I just want to expose you to this as of now. Okay? You can also have one electron transfers from, say, transition metals. This is actually pretty common. There's orbitals out here for iron. There's probably going to be one electron in some of these. Okay? There could be another electron in this orbital too. I'm just indicating one. And what can happen is this electron can be transferred to something like molecular oxygen, a very common thing that happens in biological systems. This electron can be transferred to, I guess I transferred it to that one. Notice it's a fishhook arrow because I'm only transferring one electron. So if iron 2+ loses an electron, it's losing a negative charge, which means now it goes up to a 3+ charge, right? And if oxygen, molecular oxygen O2, neutral, is gaining an electron, then it's ultimately going to go to a minus charge. And this particular ion is called superoxide, okay? You don't need to worry about that. But I just want to hopefully show you that this is how you draw mechanisms for one electron moving, okay? Now, before we do the mechanism of radical or anti-Markovnikov hydrohalogenation, I have to show you another thing that can happen. Remember, I mentioned that if I apply heat to a system with a hydrogen peroxide or an organic peroxide, or light, I can get this oxygen-oxygen bond to split. Now here's the thing. Remember, this bond between the two oxygens, remember, that's comprised of 2 electrons, just like any covalent bond, okay? So, and actually let me color code this. I'll do this one in orange over here, okay? So when I subject it to heat or light, and in this reaction we're going to use heat, but when I do that, subject it to heat, you can actually cause the bond to break, but it's going to do so using a radical mechanism. And what that means is one of these electrons, the red one, will move on to this oxygen, right? Notice I'm doing a fishhook arrow because it's one electron, just the red one. The orange electron will move on to this oxygen. Again, a fishhook arrow because it's one electron moving. And my ultimate result here is I get this. I get one of these oxygens, and it also has 2 lone pairs on it, but it also gets this red electron, right? And then I'm going to get another hydroxyl radical, but this one has the orange electron right there. Those would be my 2 products, although these electrons are identical, so technically you just write 2 hydroxyl radicals. But just so you can see where these electrons go. Both of the red and orange electrons were in this bond, but when you subject a peroxide to heat or light, one of the electrons goes onto one oxygen, the other goes onto the other. Okay, that's going to be really important when we look at the mechanism, and we're going to do that now. And this mechanism is going to help explain why this reaction is going to be anti-Markovnikov. Okay, a drink. All right. So the first thing we're going to do with the reaction is we're going to throw in the organic peroxide. So you don't really want to use hydrogen peroxide. Use an organic peroxide. Okay. So what I'm going to do is I'm going to subject this ultimately to heat. Okay, subject this to heat. Okay, mechanistic steps are going to be in green. So what I'm going to do is remember that there's 2 electrons in this oxygen-oxygen peroxide bond. When I subject this to, oops, didn't mean to do that. When I subject this compound to heat, one of these electrons is going to move on to this oxygen, and the other one will end up on this oxygen. By the way, you'll learn this in the radical chapter. That's called a homolytic bond cleavage. Okay, you don't need to worry about that right now. But notice, I generate this one, R prime, with the oxygen, and R with the oxygen. Okay, R and R prime. But now what I'm going to do is I'm going to take this radical right here. It is a radical because it has a lone electron on that oxygen, and I'm going to throw it in with hydrobromic acid. Now, something else is going to happen here, okay? Remember, this right here, this HBr, again, is 2 electrons, right? This is a 2-electron bond. They all are, okay? All single bonds are. And then what's going to happen is one of these electrons is going to essentially couple with this electron, okay? It's not technically called coupling, but just to make it make sense at this point, okay? We'll do more detail on this in the radical chapter. So this oxygen is forming a bond with the hydrogen, and then this light blue electron goes onto the bromine to make atomic bromine. But look what you did. You have this R bound to an oxygen radical, which is going to abstract the hydrogen in this one blue electron, and you get ROH, right? ROH, okay? So hopefully that makes sense. This ROH is going to come back later in the mechanism. All right, this was the first step right here. Now we're going to look at the second step. By the way, the first step was something called... all right, so here's the second step. Again, let me do this. I'm going to denote this pi bond. Put it in orange. So the white one is the sigma bond. This one is orange. That's the pi bond, okay? And I'm going to put that this electron in the pi bond is the red one, and then the other electron that's in the pi bond, the other pi electron is yellow. Okay? So what's going to happen is you can get kind of a similar thing. Okay? One of these electrons, I'm going to do it as the yellow one. The yellow one is going to couple with this electron on atomic bromine. It's going to couple with that one. So what you're doing is you're forming a bond between atomic bromine and ultimately this carbon right there because that electron's closest. And then the red electron is just going to go on to that carbon right there. Now that red electron, I've indicated it here in white, but that red electron is this one right there, okay? Now the question is, why didn't the radical, why didn't say the red electron couple with the bromine and the yellow one ended up on this carbon right there? Why not? In other words, that would have been Markovnikov. Why doesn't that happen? Well, it has to do with the mechanism. Remember when we talked about carbocation stability, and we had that concept that primary carbocations were the least stable, other than methyls. Secondary carbocations were more stable, but the most stable by far were tertiary carbocations. Well, there's an exact same trend for radicals. We would say that for radicals, tertiary are the most stable, secondary are less stable than that, primary are not stable really at all, and then your methyls or 0 degrees are by far the least stable. So that means that if I can form preferentially a tertiary radical, then that's the one that will form. And that's why you see the red radical forming on this carbon right here on the left, the more substituted position. Because if you think about it, here's 1 carbon, 2 carbon, and a 3rd carbon. So this carbon is tri-substituted. If we look at the other carbon, it has 1 group, a 2nd group, so it's only di-substituted. So that's why the carbocation forms on the left side, and the bromine will add to the right side. Okay? Then what we're going to do is we're going to throw this in with some more hydrobromic acid. Now, again, we can do kind of a similar thing here. Let's do this. This electron will be red. I don't know. Let's do this one. This one will be gray. Let's do that. Okay, that one will be gray. Then what we're going to do is a similar thing. This radical electron right here, the red one, will couple with the red one from the HBr. Okay, and that's why you see this hydrogen right here bound to this carbon. And because those 2 electrons are red, I'll just draw this bond in red. So those are those 2 electrons right there. One of the electrons was the hydrogen, the other one was from the carbon. Right? Okay. And then that's going to cause this electron, the gray one, to go onto the bromine. And so that means this bromine right here, this one right there, I'll draw that radical in gray. I'll also draw this one in gray. Okay? This other bromine right here, remember, had the light blue radical electron. It came onto this to make this. So this bromine right here is going to come back right here. So now we've generated 2 atomic bromines. And what's ultimately going to happen is you're going to get termination of the radical, which means that this lone electron, this radical, is going to couple with this one right there, fishhook arrows because it's 1 electron movement, and you just get molecular bromine. Okay? And so that's ultimately the mechanism of anti-Markovnikov hydrohalogenation. Okay? Now here's the really important thing that comes ultimately out of the mechanism, okay? And it's going to be useful whenever we start predicting products. Okay, let me come over here. If you think back to when we looked at carbocations, I'll just draw a simple one, okay, like this. That central carbon right there is the one that has the positive charge. And when carbon has a positive charge like that, in this case, it means that it has sp2 hybridization, okay? Meaning it's not linear, it's planar. Trigonal planar, but the key word is it's planar, it's flat, okay? So if you think about it like this, here's one of those carbons, and then kind of one's going to kind of go off like that, another's going to come like that, and you have this positive charge there. So that means if I had a nucleophile that wanted to attack that, remember how we talked about that there was sort of an equal likelihood that that nucleophile could attack from either side, right? Because it's flat, okay? There's approximately just as about of a steric hindrance on the top as there is the bottom. So you're equally likely that the nucleophile can attack the bottom or the top, right? Well, it's sort of a similar concept with radicals, okay? With radicals, again, they're going to sort of look like this. I'll draw the same compound, but draw it as a radical, okay? With that compound right there, okay, it's also essentially sp2 hybridized, okay? This is also essentially sp2 hybridized, which also means it's planar and it's flat, okay? So basically what that means, because it's flat, when this electron comes out and tries to couple with something else, it can couple with something above it or below it. Now, what does that mean? Well, that implies that this type of reaction is not stereospecific, meaning that you can get a mixture of products. Okay, so for example, let's say this was R1, let's say this is R2, let's say this is R3, okay? This essentially means, let me reorient you to this. Here's the carbon in the center. Let's draw R2 coming back like that. R3 is going to come like that, right? This is planar, right? Hopefully that makes sense. And we'll draw the radical there, right, like that, okay? Now, essentially, let's suppose that I have some, let's do this, a radical up there and a radical on the top, right? Well, when this couples, right, this could couple with the one on the top, or it could couple with the one on the bottom, which with approximately equal likelihood. So that means what I get is something like this. Here's the central carbon. That R group is down there. That's just simple R. And then R2, and then R3. But if I do the one from the top, then I'm going to get something like this. R1, this is the central carbon. Blue R goes on the top, but then you can see that R2 goes down like that, and then here's R3. So these two compounds are stereoisomers of one another, assuming that this carbon is chiral, and we'll assume that. So that means that because this is essentially sp2 hybridized and the radical can couple from either side, either the positive z-axis or the negative, depending on if the radical's on the top or the bottom, you can get a mixture of products. So when we draw the products over here and predict them, we are more or less going to assume that we're going to get a mixture, and we don't necessarily have to indicate stereochemistry. Okay, but we can generate chiral centers. All right. So here we have this alkene right here, okay? And remember, we're subjecting it to organic peroxide, heat, and HBr. And remember, this reaction is going to add bromine to the least substituted side, which means over here, right? That has two hydrogens, it's zero substituted. This one is di-substituted. All right. So, having said that, all we do for this is we draw this carbon over here, and then we just draw a bromine attached to it. It's as simple as that, okay? And then if we wanted to indicate the other hydrogen, we could indicate it there. Now, remember, there are also already two hydrogens there. So the question is, did we generate a chiral center? The answer is no. There is no chiral center in this molecule, so this is literally your only product. Okay, that's it. All right. So hopefully that makes enough sense. Here's another compound. Here's our alkene right there. What's the least substituted side? Well, this side has two carbons. This has one. So that's the least substituted side. That's where I'm going to add the bromine, right? So what am I going to get? I can get this. This will go there, and I'll ultimately get a hydrogen there. And I'm going to add the bromine right there. Okay? So that's where the bromine adds to the least substituted side. Now, here's an important question. Did I generate any chiral centers? Well, you generated one here, right? Because if you think about it, there actually is a hydrogen there, okay? So 4 different groups. And this one's also a chiral center. So you have 2 chiral centers. Now, the key is when this hydrogen in the mechanism adds right here, again, it's a radical, so it can add from either side, okay? So you can ultimately get this hydrogen going either direction. You can also get this bromine going either direction. So you have 2 chiral centers. You can get all possible stereoisomers. So the question is, how many possible stereoisomers do I get? Well, let's go ahead and look at all the possible ones we can get. Now, you don't have to draw all of these. This is sufficient right here. I'll go ahead and just box that. But if you wanted to look at all the possible things we could get, let's do that. So if I say put this methyl on a wedge and say this hydrogen on a dash, then I could certainly get this bromine on a wedge and this hydrogen on a dash, right? But I could also have another situation. Let's keep this methyl on a dash, this hydrogen on a wedge, but let's put this bromine on a dash and this hydrogen on a wedge, okay? What's their relationship to one another? Those are diastereomers of one another, right? Because I flipped only one of the chiral centers, right? I flipped the one on the top. So those are diastereomers. Let's draw some other possibilities. Now let's put this methyl on a wedge, this hydrogen on a dash, and let's keep this bromine on a wedge, put this hydrogen on a dash. I could have this, and then I could also have this. Put that methyl on a wedge, hydrogen on a dash, and then put this bromine on a dash and the hydrogen on a wedge. These are all stereoisomers of one another, and technically you could get all of these. Since we can get all of these, and there's not really any decent way to tell which one you can get, you just simply draw the generic one without stereochemistry indicated because, again, anti-Markovnikov hydrohalogenation is not stereospecific. The only thing it's specific for is adding the bromine atom to the least substituted side. Okay? Here's another example, similar compound. Let's go ahead and look at the alkene. Where is the least substituted side? That's this side. It has no carbons attached to it. No, it's not substituted. So that means we're ultimately going to add the bromine to that position. All right? So there we go. And then I'm going to add the bromine there. And again, there's no chiral centers in that molecule. So again, that's all you would get. And since you could get a mixture anyways, just put that. All right. Here's my last example right here. There you go. And what's the least substituted side? Well, the right side here has 2 carbons. The left side has 1. And so that's my least substituted side right there. That's the side that's going to get the bromine atom, or the bromide. Okay? So when I draw that product, I'm just going to put the bromine right there. Okay? This is also a chiral compound. I only have 1 chiral center in this molecule. Okay? That's the only chiral center. Remember, it has a hydrogen also. Has a hydrogen, a bromine, an isopropyl, and an ethyl. Now, what I'm going to do is I'm just going to say enantiomers, okay, En'(S), enantiomers, because I can get enantiomers on this one, okay. And if I wanted to draw exactly what they were, I can do that. Let me just show you. I could get this bromine on a dash, the hydrogen on a wedge, or I could get the enantiomer where I could have the hydrogen on a dash and the bromine on the wedge. Okay, so I could get both of those, but you can literally just draw this and then just say enantiomers, and that's also correct. So either one of these is technically correct. Just realize if you generate more than 1 chiral center, like in the second case here, you can actually get, at least 4 products. Okay, so something like that. All right, so hopefully these examples made sense. All you're doing is you're adding bromine to the least substituted side. It's an anti-Markovnikov addition. Okay. Now, there is one other thing I want to talk about with this reaction. Okay. Notice what I said here at the very beginning of the video. Hopefully you caught it. When I do this reaction, okay, the Markovnikov version from the previous video, and you want to add the halogen to the more substituted side, I can use HCl, HBr, HI, right? I can use all of those. I just can't use hydrofluoric acid, right? When you do this reaction, okay, you can only use HBr, meaning this will really not work with HI, and it really won't work with HCl. It's only going to work with HBr, okay? And that's all you'll use for it. Now, if you did want to get a chloride on the least substituted side, you can do that. You just have to do this reaction first, and then you can do a type of substitution reaction to substitute the bromine for a chloride or an iodide. And that's something we'll look at when we do synthesis in the chapter after radicals. We'll talk about that. But hopefully, ultimately, this reaction makes sense. All you're doing is you're using HBr, an organic peroxide, and heat, and you add a bromide or bromine atom to the least substituted side, making it anti-Markovnikov. All right. So thank you so much for watching this. Hopefully this helped out. Make sure to like the video, subscribe to the channel for future videos and notifications. Thank you very much.